well, something that truly bends the mind. We're exploring the fundamental strangeness right at the heart of the universe. It's a deep dive into quantum indeterminacy and its incredibly close relationship with the mathematical tool that sort of captures it all, the wave function. We've got your stack of sources right here, gathered specifically to help us navigate this, let's face it, complex, but utterly fascinating territory. Our goal isn't just, defining terms. We want to really get to grips with why the quantum world defies our everyday intuition and how the wave function acts as its strange blueprint. Hopefully we'll land a few of those satisfying aha moments along the way.
Absolutely. And this is really where physics stops being just about how things move around. It starts challenging our fundamental ideas about what real even means. This indeterminacy we're talking about. It isn't some fuzzy area because our machines aren't quite good enough yet.
Right.
It seems to be a feature that's just baked into the fabric of nature itself, at the very smallest scales.
Okay, so let's unpack this core weirdness then. The material we're looking at starts right off by establishing quantum indeterminacy. And straight away, it pushes back against a common misunderstanding. This isn't about sloppy measurements, is it?
Not at all. The sources are very clear on this. It's a fundamental property of quantum systems. Before you measure them, certain properties simply don't possess definite single values simultaneously.
Right. They just don't have them yet.
Exactly. And this intrinsic limit on what you can know at the same time is most famously summarized by, the Heisenberg uncertainty principle. It puts a kind of non-negotiable boundary on how precisely you can determine certain pairs of properties for a particle together. Think of them like partners, maybe. They can't both be sharply in focus at once.
Okay. And the classic examples the sources point to are position and momentum. The principle basically states there's this trade-off. The more precisely you pin down a particle's position, let's call that uncertainty, the less precisely you can possibly know its momentum, ergot, and, vice versa. This is captured by that famous inequality. Xip has to be greater than or equal to 2.
H bar over 2.
And there's another pair mentioned too, energy and time, Xi 2. Now, H bar, that's just this tiny, tiny constant setting the quantum scale.
Right. It's incredibly small, but the principle holds.
But the crucial insight here isn't just how small is, it's the inequality itself, isn't it?
Exactly.
It's telling us that the uncertainty in one property actually forces uncertainty in its partner. So it's not that the particle has a definite position and momentum that we just can't find precisely.
No, that's the key misunderstanding.
It's that before measurement, it just doesn't have both simultaneously in a precisely defined way.
That's the core of indeterminacy. So if properties aren't definite before you measure them, how on earth do you even describe a quantum system?
Yeah, good question.
This is where the wave function comes in, usually written as the Greek letter psi. It's the central mathematical object. The sources describe it as the complete mathematical description of a quantum system's state. And it's not a simple number. It's a complex valued function often called a probability amplitude.
A probability amplitude.
Yeah.
Okay, that sounds like a bit of a mouthful. What does that actually mean? What information does this wave function hold?
Well, what's fascinating, and what the sources emphasize, is that the wave function contains everything that can be known about the system at any given moment. Crucially, before a measurement happens. It doesn't give you, a list of definite values. Position is X, momentum is Y. Instead, it holds the potential information about all the possible properties, its possible energy states, possible momenta, potential positions, spin orientation, stuff like that.
So it's a summary of all the possibilities.
Exactly. A blueprint of potentiality, you could say.
Okay, so it holds the potential. How does this blueprint of possibilities, how does it change over time? Does it just evolve randomly?
No. And this is another really key point the sources make. As long as you're not interfering with the system, by trying to measure something, the wave function evolves completely smoothly and deterministically.
Deterministically. So predictable.
Yes. Its future state is precisely dictated by its current state, and it's governed by the Schrödinger equation.
Ah, yes, the iconic Schrödinger equation. I see a source is provided here. IUA H-E-G.
That's the one. Looks a bit intimidating, maybe.
It does. We don't need to dissect every symbol right now, but conceptually, this equation is kind of like quantum mechanics' version of Newton's laws, right? EFMA.
That's a great analogy, yeah. It tells us how the system's state, its wave function, its whole landscape of potential changes predictably as time passes. The absolute key, though, is that this evolution is continuous and deterministic unless something external, like a measurement, interacts with it.
Right. The measurement is the disruptive event.
Exactly. And it's precisely this wave function that embodies the indeterminacy we were just talking about, specifically through the principle of superposition.
Superposition.
Yeah.
Okay, this is where things start to feel, well, truly bizarre for our everyday brains. What does it actually mean for a system to be in a superposition?
It means the quantum system can exist in a combination, like a blend, of multiple possible states simultaneously.
Simultaneously.
Yes. The sources use the example of an electron's position. Before you measure where it is, it's not definitively at one single point. Its wave function describes it as being in a superposition of many potential positions all at once, sort of spread out in space, almost like a wave, hence the name wave function.
So it's not just that we don't know where it is, it's somehow actually existing in multiple places or multiple states at the same time. That's the weird part.
That is the weird part. It's a state of being in a combination of possibilities. It's not just about our human ignorance of some single hidden reality. It's fundamentally different. Mathematically, this is shown by writing the wave function as a sum, like AA plus O plus CO and so on, up to Che.
Okay.
Here, the A, those represent the individual possible states, like maybe being at position A or being in energy state B. And the CA, those numbers are the complex probability amplitudes we mentioned earlier.
Right, the probability amplitudes. And how do those C numbers relate to what we might actually, observe if we looked?
Well, that's where the probability connection comes in directly. You take the magnitude of each coefficient, con, and square it. So in Schoener, that value gives you the actual probability of finding the system in that corresponding state, A, if you perform a measurement designed to check for that state.
Okay, so the wave function is this blend of possibility. And the coefficients tell us the likelihood, the probability of each possibility being the one we actually see when we finally look.
Precisely.
So this blend of possibilities, this sort of spread out nature, how does that link back to the uncertainty principle trade-off we talked about between, say, position and momentum?
Oh, it links beautifully. It has to. The spatial spread of the wave function in position space directly reflects the position uncertainty. If the wave function is spread out over a large region of space.
Big uncertainty in position, large function.
Right. Now, the uncertainty principle demands that if AK is large, then the momentum uncertainty must be small.
Okay.
So how is that captured in the wave function?
Yeah.
It means that this spatially spread out wave function must actually be built from or be a superposition of momentum states that are all clustered very closely together in value, a narrow range of momenta.
Ah, I see. So wide in position means narrow in momentum.
Exactly. And conversely, if you have a wave function that's very localized in space, like a sharp peak, meaning a very small x, you know its position precisely.
Then the uncertainty principle demands a large, high momentum uncertainty.
Correct. And that corresponds to this localized wave function actually being a superposition, a blend of many different momentum states widely spread out in value. So the wave function is the mathematical description of this probabilistic distribution of possibilities that inherently satisfies the uncertainty principle trade-off. It's all built in.
Okay, I think I'm following. The wave function is this dynamic blueprint of potential, obeying the uncertainty rules. But what happens when you step in and actually look? You perform a measurement. That's the missing piece.
Right. This is the dramatic moment in quantum mechanics. It's the process known as wave function collapse, or sometimes state reduction. When you measure a specific property, say, position that smooth, deterministic evolution of the superposition according to Schrödinger, it just abruptly stops.
And what replaces it? Does it just disappear?
No, it instantaneously changes. It collapses.
Yeah.
It goes from being that spread out superposition of multiple possibilities into just one single state. Specifically, it collapses into the state corresponding to the particular outcome you just measured. So think of the example from the sources. If the particle's wave function was a superposition of being maybe at positions A, B, and C, and your measurement finds it at position A,
Quick, it's at A.
exactly. At that instant, the wave function snaps to only being the state at position A. The potential for it being at B or C just vanishes. Gone.
Okay, so the indeterminacy for the property you just measured, position,
Mm-hmm.
in this case is resolved. Bang, you found it. But does that have consequences for the other properties? Does this tie back to the uncertainty principle again?
Absolutely. This is where it all connects back. Beautifully and consistently. The very act of forcing the wave function to collapse into a single definite value for one property. Let's say you got a very precise position measurement, meaning a tiny, that means the wave function after the collapse must now satisfy the uncertainty principle for the other complementary variables.
Like momentum.
Like momentum, a wave function that's now sharply localized in space, tiny e's, must necessarily be a very broad superposition of many different momentum states, large L.
So by getting that definite position, you've just automatically, dramatically increased the indeterminacy of its momentum.
You have. The collapse enforces the trade-off. You gain knowledge of position at the expense of knowledge of momentum.
Wow. And this leads directly then into why quantum mechanics fundamentally predicts probabilities, doesn't it? The whole probabilistic interpretation based on the Born rule.
Exactly that. Because the state before you measure is this superposition, this blend of possibilities with associated probability amplitudes encoded in the wave function. We simply cannot predict the outcome of any single measurement with certainty. It's impossible in principle, usually. We can only predict the probability of getting each possible outcome.
And the Born rule is what gives us the actual recipe for calculating those probabilities.
Yes, precisely. As the material mentions, the Born rule tells us how to get from those complex probability amplitudes in A to the real, measurable probabilities you'd see in an experiment. For continuous properties like position, the rule is the square of the magnitude of the wave function at a particular point gives the probability density of finding the particle right there.
Probability density.
And for discrete outcomes, like maybe measuring which specific energy level the particle is in, it's simpler. Just the square of the magnitude of the amplitude coefficient for that specific state. That gives the probability.
And the fundamental insight here, the big takeaway.
It's that quantum mechanics inherently provides probabilities, not certainties, because the underlying reality it describes before measurement is one of indeterminate possibilities. It's all captured by the wave function's superposition. If systems really had definite values for all properties all the time, hidden away somehow, then the theory would generally predict certainties. But it doesn't.
Because that's not how nature works at this level.
Seems not. Nature at this scale seems fundamentally probabilistic because of this indeterminacy.
Okay, so let's try to quickly wrap this loop up just to solidify it, based on how we've traced it through the material. First, indeterminacy is fundamental. It's not about us.
Right. Baked in.
Second, the wave function embodies this indeterminacy through superposition. It describes a blend of potential states.
Holds the possibilities.
Third, measurement forces the wave function to collapse into just one of those states, giving a definite outcome for the property measured.
The dramatic moment. Yep.
Fourth, this collapse automatically means the wave function must now reflect increased uncertainty in complementary properties, perfectly satisfying the uncertainty principle.
The trade-off is enforced.
And finally, the wave function, through the Born rule, is ultimately our mathematical tool to calculate the probabilities of those different outcomes, reflecting this deep, built-in indeterminacy of the quantum world.
That's a great summary. That's the coherent picture our sources are painting. A world where the blueprint isn't a snapshot of fixed reality, but this landscape of potential, until the act of observation steps in and makes it choose.
Wow. Okay. We've journeyed quite a way there. From understanding that quantum uncertainty isn't about bad equipment, but a fundamental feature, to seeing how the wave function describes systems as existing in this truly mind-bending state of superposition, and then how the act of measurement forces a choice, collapsing that wave of possibilities into a single outcome, but with these unavoidable consequences for other properties.
It really is a picture of reality that's fundamentally different from our macroscopic experience, isn't it? A world where probabilities aren't just, due to us missing some information. They seem to be a core part of its actual structure.
And here's where it gets really interesting, and something the sources kind of implicitly touch on, leaves you thinking. If the wave function genuinely describes a system as this spread of possibilities before you measure it, well, what does that actually mean about the reality of that particle when nobody is looking?
The big question.
Does a particle, genuinely not have a definite position until the very moment you perform a measurement? Is it truly smeared out? That leap, that transition from a state of superposition, of indeterminacy, to a single definite outcome via measurement.
A collapse.
Yeah, the collapse. It's still one of the deepest mysteries and biggest points of debate in physics.
Absolutely. What is measurement? Does consciousness play a role? Decoherence? Many interpretations.
It really leaves you wondering about, the role of the observer, or interaction, in shaping reality itself.
Yeah.
Definitely something for you to mull over on your own deep dive after this.